Thank you very much to the organizing committee for extending the invitation to present our research at the Photothermal webinar 2023. Today, on behalf of my team, I'm excited to share our findings on photothermal spectroscopy involving nanomechanical silicon nitride resonators that are drawn from both our research team at TU Wien and the endeavors of our startup, Invisible Light Labs. I will start from the angle of our research team at TU Wien. As you can see here, this is a team that's behind the results I'm going to present you today. Before that, I want to quickly introduce again why photothermal sensing is actually has advantages over transmission measurements, for example, or other traditional ways of doing spectroscopy. And it's all about the signal-to-noise ratio enhancement. If we consider a transmission measurement, we have a sample and we illuminate it with probing light with power Pi. And in the back, we detect the light that's being transmitted. We assume, among others, that the sample is absorbing just a small amount of light, and then the absorbance, which is the ratio of absorbed power to irradiated power, is a lot smaller than 1. And also, having taken this assumption, this leads to a transmittance which is more or less equal to 1, since the absorbed light is negligible. Under these circumstances, we can write down a simple term for the signal-to-noise ratio, neglecting reflection and scattering and so on. And when you write this down, the signal in this case is then given by the absorbed power, the power of the light that's absorbed by the sample, divided by the noise. And the noise here is the fractional intensity noise of the light source or of the system itself. And it scales with the transmittance because we measure all the light that's transmitting, and hence we also measure all the light noise that is carried by the light sourse. And this gives us this value for the signal-to-noise ratio, which is then the absorbance divided by 1 over the square root of SI, the fractional intensity noise power spectral density. In contrast, photothermal has an advantage because here we absorb the probing light. And this gives us a better scaling law. In this case, if we write down the signal-to-noise ratio term, again, the signal is the same. It's the absorbed power. But the noise is now only the noise that of the fraction of the light that's being absorbed. And hence, we have there a factor of alpha instead of a t at the bottom. And this gives us a signal-to-noise ratio in the following form, which is 1 over square root of SI. And you can see that, assuming, again, that it's a small sample, you can see that the signal-to-noise ratio is orders of magnitude better compared to a transmission measurement. And this is, of course, why we have the so-called signal-to-noise ratio enhancement, which is 1 over alpha. And again, if alpha is very small, we gain a lot by doing photothermal measurements compared to transmission measurements. Of course, there's a way around. We can do balanced scheme, a balanced transmission scheme. And this requires a bit more devices. This is a bit more sophisticated to set up, but it's doable. And here we basically subtract all the noise if it is correlated from the light source. And by subtracting it from the measurement signal, we can get to the same signal-to-noise ratio as we would get with the photothermal measurement. Of course, the fundamental limit here are quantum noise, such as shot noise, which will be uncorrelated and cannot be subtracted by a balanced scheme. And yes, so with the balanced transmission scheme, we have in theory the same signal-to-noise ratio. It's not only theory, it's also been shown, and it's this very famous paper from Celebrano et al., where they have actually shown that that it's possible to measure the absorption of a very small absorber, in this case, an individual molecule, by implementing a well-balanced detection scheme. Here you see one of their pictures where the black little dot in the center, this shade, is representing missing light from a molecule that has absorbed it. And in their case, this SI is indeed shot noise. At the same time, of course, another technique has shown to be able to reach the single molecule regime by the team of Professor Oret. And this is the photothermal microscopy scheme, which the whole webinar is all about. And you can see these signals in this plot represent individual molecules. So how is traditional photothermal microscopy performed? We have some kind of a sample that we pump with a laser. We heat it up. And this heating causes also a heating of the vicinity of the material, the medium, or the substrate in the vicinity of the sample. This causes a change in the optical properties, which can be picked up by a second probing laser. In contrast, I would like to introduce today nanomechanical photothermal microscopy, which uses the substrate itself as a temperature-sensitive element. In essence, the substrate acts as a thermometer, and we do not need a second laser to pick up the change in optical properties. This is a schematic how this works. We have, for example, a string resonator. On this string resonator, we have something that absorbs light, a sample. This can be a nanoparticle, it can be a molecule. We then measure and let it ring at a specific mode frequency. When we probe this absorber with light, this sample will heat up. The photothermal heating causes the string also to heat up and expand a little bit, and this expansion causes a measurable frequency detuning, as you can see schematically here to the right. Pretty much 20 years ago, this is what we did when I was in Denmark. You can see here a SEM image of a silicon nitride string that is covered with a few polystyrene nanoparticles. When we scanned over the surface with a laser and simultaneously measured the frequency of a specific mode, a mechanical mode of this string resonator, we could observe that the frequency of the mechanical mode detunes every time our laser hits or crosses over one of these nanoparticles. We are also able to show a year later that we can do this with plasmonic nanostructures such as plasmonic nanorods or also plasmonic nanoslits. Later, we moved on to the 2D structures. We call them drumheads or membranes made of silicon nitride. They're roughly 50 nanometers thin, so very thin, but relatively large laterally. I'm speaking of hundreds of micrometers to millimeters. And this gives us more space, especially to make 2D scans. You can see here schematically our work from 2018, where we placed a sample, for example, 10 nanometer gold nanoparticles on such a drum. And again, when the probing laser hits one of these particles, the particle will photothermally heat up the drum, and the drum will detune in its mechanical frequency. This is a scan over such a drum, and you can see that the frequency on the y-axis has two dips, and these two dips correspond to two particles over which the probing laser was scanning. After some background correction and integration, we get the same data cleaned up in the second plot, and this data represents one scan line. We can then now put together and build up these scan lines to a 2D image that you can see here of 10 nanometer gold nanoparticles with a relatively good signal to noise ratio. Later, we pushed this system to the ultimate limit, where we were able to record the absorption of individual molecules, the signals 1, 2, 3 representing these molecules, and verified by fluorescent microscopy, a standard and state-of-the-art single molecule technique to prove that these molecules were indeed there. Let's talk about the performance. How is it possible to get such a high sensitivity that allows us to measure the absorption of individual molecules? I would like to introduce the responsivity. The responsivity to power RP is the fractional frequency detuning per absorbed power. We can change the term a little bit and write it as the responsivity to temperature, RT, divided by the thermal conductance, G. I'd just like to mention this transfer function H, TH, is a low-pass filter that is coming from the thermal time constant of the mechanical resonator. We can actually derive a term, a closed form solution for a mechanical drum head, as it is shown schematically to the right. And again, we can find again a value for the temperature responsivity in green. And if we look closely at this temperature responsivity in green, we find something that I call an enhancement factor, which is the ratio of the Young's modulus divided by the tensile stress of our drum head. We have been working with silicon nitride that has a Young's modulus of several hundreds of gigapascal. And for the single molecule measurements that I showed you previously, we tuned the tensile stress down to 1 megapascal. So this enhancement factor is reaching almost 1 million. So this is one of the reasons that behind this high sensitivity, this high response to change in temperature of these drum head resonators. We recorded this the responsivity for different drums with different sizes, as you can see here. The measurements are the dots, and we also have the model as lines. You can see two regimes. One is a conductive plateau, which comes from the regime where the membrane is the heat transfer of the membrane is dominated by conduction. And in this case, the responsivity to power up is independent of the size. So it is a plateau. But as you can see, this is not what we measure. We measure actually a drop of the response for larger membranes. And this is because suddenly the membrane starts to couple to the environment through radiative heat transfer. And this causes the temperature in the center of the drum to reduce for larger membranes. And it's a temperature change that causes the frequency detuning. So the responsivity of a square drum head is plateauing for smaller sizes and then decreasing for larger sizes because we enter the radiative heat transfer regime. These square drum heads have a relatively low responsivity, but they offer a relatively large absorption or sampling area. In contrast, a string, as shown here schematically, improves with the responsivity for longer lengths until we reach the radiative heat transfer regime, and then again the responsivity starts to drop. So strings offer a high responsivity but a small sampling area. The sweet spot is what we call a trampoline. A trampoline behaves similarly to a square drum head. We have a little center area that is big enough to actually do scans and sample enough material, but it comes with a high responsivity that we will only get with a string, and combining it with a relatively large area that we can work with for microscopy and in particular spectroscopy. So the responsivity is only half of the equation. The other half, of course, is the noise. And we determine our sensitivity by the noise equivalent power of our system. The NEP is given by the square root of the fractional frequency noise power spectral density, SY, divided by the power responsivity, as introduced before. And the fractional frequency noise power spectral density, SY, is the sum of different mechanisms. One of them is thermomechanical noise. It is the thermal vibration of the mechanical resonator that's introducing phase noise into our system. And the second contribution, noise contribution, is coming from thermal fluctuations of the resonator that causes frequency noise. And We can calculate both terms and predict the ultimate NEP that we can measure. And here, for example, you can see the NEP for a string resonator of different lengths. You can see that for shorter strings, thermomechanical noise will limit our NEP. And then there's an optimum for a length of about 1 to 2 millimeters, where we are actually limited by the temperature fluctuations of the structure itself. If we make the string very long, we enter the regime where the heat transfer is fully dominated by radiation. And in this case, our noise is determined by the thermal photon intensity noise. We can improve the NEP by cooling the system. Cooling has two effects. Cooling reduces the heat exchange via radiation, so the responsivity is not limited by increasing the size of the resonator. And more importantly, it lowers the thermal noise sources. You can see here some predictions for 77 Kelvin and 4 Kelvin. You can see we can reach the single-digit femtowatt per squared hertz NEP values. We are now at the point where we really believe we fully understand all the noise processes in our resonators. This is the data of our frequency noise analyzed by its Allen deviation. You can see the Allen deviation sigma y on the y-axis as a function of the integration time tau. This is a measurement of a 1 millimeter by 1 millimeter square membrane, 50 nanometers thick silicon nitride. And these are our estimated or expected noise contributions. Blue, thermomechanical noise. Red, temperature fluctuation noise. And the purple line is frequency noise introduced by intensity fluctuations of the probing laser. If we sum all these noise contributions up, we end up with this black curve, which really fits the measured green curve very well. So the noise equivalent power is something we can actually predict with relatively high accuracy. So the NEP of a string is plotted here. We can see we can reach femtowatts per squared hertz for sizes of the order of a millimeter. And we can also do this for square membranes. You can see square membranes have a relatively higher NEP compared to strings, but again, offering, of course, more area to work with. Again, our best compromise is a trampoline where we reach a few femtowatts per squared hertz NEPs, and we can make the center area relatively large before we start to be limited by photon noise. That is actually the noise coming from the photon exchange with the environment. This is how such a trampoline looks like in a photograph. And we have done some microscopy with these. You can see here a reference, and we also use these as IR detectors when we coat them with a broadband IR absorber, and we can reach NEPs of 7 picowatts per squared hertz, which is a record number for a broadband infrared 2 terahertz detector. But I would like to move a bit on to what else we can do, because I want to present you that we can also perform real photothermal spectroscopy. I would like to highlight that these structures are very robust and allow all kinds of sampling, from dipping them into liquids, from drop casting liquids or dispersion, spin casting, evaporating samples onto them, impacting samples onto the silicon nitride drums, and so on. You can also transfer 2D materials on them. They will survive most of these sampling procedures without breaking. So we can actually analyze a wide range of samples. Also, because we are intrinsically blind to or agnostic to the wavelength with which we probe the sample on the drum, we can cover a huge spectral range. And this is an overview over different samples: thin films, particulates, molecules, 2D materials, single nanoparticles, and even single molecules that have been probed from all the way from the UV all the way to the mid to far IR. with the same silicon nitride system. So we have a huge spectral range. I would like to start in the UV-Vis regime. Here, this is a collaboration with the team of Kirill Buletin from Berlin, where they transferred 2D materials, in this case tungsten disulfide, onto our silicon nitride drum heads. And they probed these 2D materials with UV-Vis light, able to measure the absorption or the photothermal spectrum of tungsten disulfide where multiple peaks are visible that they could clearly assign to very specific exciton species. And they were able to calculate an NEP of the order of 890 femtowatt per square root hertz. So you can see this is a really neat platform for 2D material characterization. I'd like to move on to VIS near IR spectroscopy that was performed in our lab. We have here two light sources. We have a visible light source in the green, and we have a tunable light source that goes from 700 to 1000 nanometers. With these light sources, we probed gold nanorods with a nominal absorption, a plasmonic absorption in the longitudinal localized surface plasma resonance of around 880 nanometers. You can see the data. We were able to extract the absorption cross-sections of individual nanorods and also of aggregates of nanorods in blue. And this is interesting. We can then actually create the sum of a spectrum of the sum of the individual and the aggregated nanorods, and we can observe a blue shift of the aggregated nanorods, which is something that is expected from theory. So you can see this is again a nice tool for nanoparticle analysis. I would like to move on to mid-IR spectroscopy. Here you can see again a silicon nitride drum that is interfaced with a quantum cascade laser that's tunable in the mid-IR fingerprint region, with which we were able to measure, for example, molecules such as caffeine on top and theobromine at the bottom with high resolution. It's also interesting that we can observe this. It can do time-resolved spectroscopy, and during over the time for a certain temperature, depending on the volatility of the sample will desorb and slowly leave the drumhead resonator, and you can see how the spectra start to fade with time. Caffeine is more volatile than theobromine to the right. You can see that already at 7.5 degrees Celsius, we can observe this fading of the signal.
2 minutes, Professor Schmid.
Yes. This allows us to measure an LOD, and we are able to record LODs of a few picograms of sample material. So in essence, we moved IR spectroscopy, which used to be easy to use, portable and cheap, but having a low sensitivity. We're able to push this to the sensitivity level, basically, of a mass spectrometer, and which was mentioned recently to be a rebirth for IR spectroscopy. These 2 minutes, of course, I would like to finish by mentioning our startup. We believe this is a very strong technique, which will allow the analysis of lots of interesting samples. So we started the startup Invisible Light Labs, and you see the team here that we have been able to create. And this is Emily, our nanomechanical FTIR spectroscopy module that is based on our nanomechanical sensor technology that is compatible with a regular FTIR spectrometer. These are the chips, and here we work with drum heads that are perforated in the center. And the reason that we work with drum heads is because this allows us a very efficient sampling technique of nanomaterials. You can see to the left the schematic of such a drum head with the perforation. Now we aspirate the nanoparticles and pull them through the perforation where they are captured with high efficiency. And once the nanomaterial is captured on the drum, of course, you know the trick. We drive it at resonance, we illuminate it with infrared light, and if we hit molecular vibration, the sample will heat up, giving us a measurable signal. So with this technique that we call EMILY, we are able to analyze minute amounts of aerosols, nanoplastics, nanomedicines, nanoscale contaminants, but also non-volatile samples such as thin films, biomolecules, or arbitrary nanomaterials. Why is this interesting? Because, for example, for urban aerosols, you can see that the mass concentration is maximum for particles larger than 100 nanometers. And this is the line in blue. However, the number concentration has a peak in the ultrafine nanoparticle sizes, smaller than 100 nanometers. And the problem is, and the remaining problem is, even though the number concentration is maximum, the mass of these ultrafine particles is so small that it's insufficient to make a standard spectroscopic analysis of chemical analysis of this material. And so there's really no other technique right now on the market to analyze ultrafine nanoparticles with high throughput. And this is where we are positioning ourselves with EMILY FTIR. We have a high throughput and we're able to measure particles between about 10 nanometers to 1 micrometer. I quickly want to show you two examples. Here you can see how such a resonator looks like after sampling of city air from Vienna, before and after, for 10 minutes. And this is the spectrum that we can extract from these measurements of aerosol ultrafine particles, which have not been accessible with standard techniques so far. But also nanoplastics is a big issue these days. Microplastics are everywhere, but microplastics will break down to nanoplastics. They are dispersed in liquids, in water, but they also are traveling in the air and stay in the air for days or months or years. And we know that nanoplastics are penetrating our body. They have been found in placenta, in breast milk, in the brain, in cells. Basically, we are full of nanoplastics. But it has remained, because of this mass issue, a real challenge to chemically analyze and find the source of these nanoplastics. So we nebulize them if they are in dispersions. We sample them on our silicon nitride resonators, and we are able to record beautiful spectra of nanoplastics with a high sensitivity. These were 54 nanometer polypropylene nanoparticles, and we sampled for only 1 minute. So this is quite a breakthrough, and I think in time, just in time, maybe hopefully for one of two of your questions. And I thank you very much for participating to this webinar.
Yeah, thank you for your nice talk. There are quite a number of new results, exciting research. So we are open for questions. You can write your question in the chat, or you can directly speak. Yes, I think we have already a question from Marcus Anton. Yeah, go ahead.
Hi, thank you. Thank you for the talk. I was a bit confused. Maybe I missed the point because you start with the laser and with the shadow, but at the end, your sample is the average over all molecules and all particles, and it's an ensemble average because they are on the chip and you get the resonance from the chip, isn't it?
This depends on how wide they are spread and how big your probing laser is. If you are able to only probe one molecule or one particle with your laser, then this is all you see. If you're in IR, the laser spot is large. There we get the average, yes.
Okay, but anyhow, it's not possible just to get the image. You get the point spread function and then the convolution of the laser profile and all the optics and so forth.
We can deconvolute it and get a quite good localization precision in the angstrom. The reason is that even though our beams cross sections as maybe a beam width is maybe a micrometer,
yep,
the signal to noise ratio is very high, so we can really, by fitting a Gaussian over our signal, we can really pinpoint the location of a sample with high precision.
Ah, cool. Thank you.
Mm-hmm.
Okay, Randy has a question.
Yeah, thanks, Silvan, for this beautiful work. Would you mind going to the slide where you show the spectrum of caffeine and the caffeine derivative?
Yes.
So as you were explaining the slide, you talked about how you can see the caffeine. I think it's the next slide when we show the time course. Yeah, this is so cool. Over time, you talked about the volatilizing these molecules, but the spectrum is also shifting over time. You have sort of new bands growing in, particularly on the left side. And I was curious just to know what was happening there.
That's very interesting. What is happening there is these are residual gas molecules and compounds that adsorb over time. So we can measure, do a residual gas analysis in vacuum and see what's adsorbing. Because now for caffeine, the temperature is below room temperature, and then we have adsorption on the resonator, on the detector. To the right, and with theobromine, we have to put the temperature higher because the volatility is lower, and there we have no adsorption.
Got it. Thank you.
Okay, Frank.
Yeah, thank you, Silvan. I have a question. You said you can also dip them into liquid, but essentially you cannot have any kind of liquid on top of them, right? Because you would get then probably effects of the evaporation and things like this.
Yes, if you have liquids on top, it will evaporate quickly. What we have built in the past are hollow resonators.
Yeah.
The liquid is inside the resonator. This works, but I have not been pursuing this path in my group so far. We are looking into covering samples, particular for protein analysis, where we need a few layers of water molecules such that the protein is able to keep its functional form.
Exactly.
It doesn't take a lot of water to make these measurements. It just needs a little shield.
So maybe another question: what are really the temperature changes you have at the end? Silicon nitride is highly conductive or thermally conductive, so I guess everything is very tiny in temperature-wise.
You mean the maximum delta T's that we measure?
Or the typical ones you have actually, which result in the detection you have.
They can range from microkelvins, millikelvins, all the way to tens of kelvins. It really depends. We have a huge range. Depends on the laser power. How much does the sample allow you before to how much temperature can it take? So the silicon nitride goes all the way up to, you can work with 1000 degrees Celsius. That would probably be fine for the silicon nitride, but not for the sample, right? So
all the properties of the material change, even non-linearity over that range, or?
Yes, of course, everything changes. Also, when we cool down, things change. But we have measured silicon nitride, and the responsivity remains relatively constant all the way down to a few kelvins.
Okay.
So the cooling is an option.
Yeah, thanks.
Okay, we take a last question from Michel.
Yes, thank you, Mr. Chairman. Yeah, very interesting talk. I was wondering about the thickness of the silicon nitride membrane.
Mm-hmm.
And in regard to your optimum of 1 millimeter, very naively, I would think, this 1 millimeter is much larger than the nano objects you are measuring. So I would imagine that it's an advantage to make the device smaller at all. So why is that wrong? I mean, apparently a big device can be more sensitive than a small. Is that because of thermal noise, or what is the key there? What am I missing?
It depends on the application. You're correct. So they are about 50 nanometers thin. They can also be a bit thinner, maybe 30 nanometers. And we make them large. For the infrared, the étendue is relatively bad. So it's hard to focus a thermal light source down to more than a few hundreds of micrometers. So we need a certain size. For the single molecule measurements, you're correct. We could go lower, make them smaller. What we lose when we go too small is that it's a trade-off between the amplitudes become smaller, the readout becomes more difficult, so noise creeps in. It's easier for us to measure larger resonators with larger deflections. You can see that the NEP is usually an optimum for the string at around 1 millimeter. we write for a square drum head or for the trampoline, it does not matter. Then we could be a lot smaller. And it has been shown that just a few tens of micrometers large, for example, graphene trampolines can be very sensitive. Yes.
Okay, thank you very much.